So good afternoon, everyone. I'm Terry Sanger, and welcome to EECS 298, Machine Learning Theory. I apologize for not being here live, as it were, for our first class. Unfortunately, I have a conflict with a meeting being organized by the National Institutes of Health, but what I'm going to do is this class will run from 3 to 4:15 normally, and then following each class, there will be a questions. I apologize, 2 to 3:15. I'm sorry. What I'm going to be doing for each class is we'll have class from 2 to 3:15, and then immediately after class from 3:15 to 4 o'clock. Are essentially office hours, and what that means is I'm just going to leave the Zoom open, and when I finish the lecture, that will be a time when it's optional. You can sign off at that point, but if you have additional questions, or if you would like to have if you'd like to have some additional information about the class or any particular issues you want to describe, I will be there, and I will continue to do that. And in particular today, I will be there by 3:15. So the first part, this part is taped, but then log on to the Zoom at 3:15, and I will be there, and we'll be able to talk about the lecture. There's a few nuts and bolts to the class. The syllabus gives lots of the information about it. The lectures are going to be on Mondays and Wednesdays, 2 to 3:15, immediately followed by office hours. The textbook is Simon Haken's book, and again, that is in the syllabus. And let's see if I can just bring up the syllabus here in case there's specific questions about that from people. Just get all the various pieces from my different computers here. Okay, here we go. Bring up the syllabus. So Simon Haken, Neural Networks and Learning Machines. This book was last printed in 2009. So there are going to be some more recent algorithms that aren't in there, and I will give you papers on that and talk about that as that happens. The intent of this course is that we will cover a lot of theory. My understanding of many of the machine learning offerings at UCI and elsewhere is that they're very much on about the practice of machine learning, meaning that you'll look at the specific software packages and how to use them with some understanding of where they're coming from and what the different types of algorithms can do. What I'm going to focus on here is really the derivation of the algorithms, where they come from, both historically and from a mathematical point of view. How you can understand which algorithms converge, which are more important, which are less important, and hopefully give a real intuitive understanding of what the different algorithms do and how they can be applied. The goal here is that you would come away from this being better prepared to invent your own algorithms and find ways in which you can push the field forward. This is a field that has been heavily dominated by ideas from physics, particularly thermodynamics. It's been heavily dominated by ideas from statistics, mathematics, differential equations, and linear algebra and multivariate calculus have tended to be a big part of this. There's a significant component from functional analysis that also has come into this, and I will be teaching some of those concepts as we go. The Haken book does not go into full depth on that, although it does cover many of the broad areas, including information theory. I don't expect you to have strong background in all of these. I will explain this as we go. I would like people to be comfortable with basic differential equations. You have to be comfortable with multivariate calculus, basic algebraic concepts such as eigenvalue decomposition, singular value decomposition, but not necessarily much computer science. This is really, although this is computer science, it's the study of distributed architectures or the connectionist architectures that dominate this much of the ways that the machine learning and neural networks group has evolved. Those are actually, of course, very different from the computational von Neumann architecture. And I am going to very much motivate this from a neural networks theory of neural networks, the idea of distributed computation, and these are distributed representations. And again, we'll go through a lot of these, but again, they're just to sort of put this in the context of other types of classes. Artificial intelligence over the years has meant many different things to many people. It started out being the idea of machines that could represent knowledge as a series of if-then statements. It was very discrete types of knowledge with what might have been called expert systems. That has fallen by the wayside, and now the words artificial intelligence are being used for what was once called connectionism. So there's lots of terminology, and we'll go through that. But again, I want to put this in the context. I am very much in the connectionist viewpoint of machine learning, and we'll very much be talking about those kinds of theories, the kinds of ways that we could understand how do brains solve learning problems, how do brains solve computational problems, what kinds of special features do these distributed algorithms have, and we will look very carefully at that. This is not going to be focused on specific applications. So for instance, I'm not going to cover in any kind of depth natural language processing, image processing, although certainly people are welcome to use those as examples or as final projects. The grading for this course is the 20% homework, 40% on the final exam, and 40% on a project. The projects, you're free to use any data set you like to come up with any interesting thing you like. I will give you some further ideas as to standards as to as we go along on this. The expectation is that a project will be the equivalent of about 10 to 20 hours of work. I will want a description of that. And again, I'll talk a little bit more about that. You can do the projects anytime during the quarter. The grading on the project is going to be on a mixture of effort and quality. I'm happy to suggest topic areas for people. To give you some sense of my background, I'm a child neurologist. I also I'm an electrical engineer, and my own interests come from the application of these methods of neural network and connectionist methods to understanding control theory. That's because many of the children that I study as a neurologist have cerebral palsy, which is a failure, an injury to the areas of the brain that permit movement. And if you're going to look at the injury to these areas of the brain, the control algorithms in humans are implemented in distributed networks, and the ways in which they are injured are things that are specific to distributed networks. So you have to understand the architectural level in order to understand how things break. So that's where I'm coming from in my interest in this. And as a result, if people come to me with particular problems, or if they need a problem area that they can focus on for their final project, I'm likely to suggest things that are going to come out of understanding human brains, modeling human brains, and possibly modeling things in robotics and control. I also have access to large data sets from Children's Orange County, which is, I'm 50% at Children's Orange County and 50% in electrical engineering. I have access to data sets both from the regular medical databases as well as the imaging databases, as well as some electrophysiology brain recording databases, and I can provide de-identified versions of those to students who are interested in working in those areas. And in fact, I would encourage you to. I would very much like to have machine learning and artificial intelligence applied to real problems that affect children and that can improve their lives. So that's a rough idea of the final projects. The way I've set up the syllabus, and if you may or may not have this in front of you at the moment, but the syllabus, you'll notice that I'm trying to bring it up here myself. Excuse me a second, because I want to be able to read this properly off of here. So on the syllabus, you'll see that each class there's reading assigned in Haken, and the reading on each line is the reading that's due that day. I expect you to have it completed. So for instance, for Thursday, you're expected to read pages 1 through 65 in Haken. We're actually going to cover about the first 40 pages in the next hour. And you'll note, and there's going to be a homework problem selected from that reading that's due on that day. But you'll notice that the way it's happening is I'm not covering the material. The reading that you're doing, I will discuss the reading in that class. So the lecture will be about the reading. In other words, you will complete the reading before each class, and then we will discuss the reading in that class. That means that you may not fully understand it. And I will explain it at that point. And it also means that the homework based on that reading is due before the class where I'm going to teach you about it. So how does that work? How could that possibly be fair? In other words, you were asked to read and do homework on something I haven't yet taught you, and then I will teach you. And so what I want you to do is I want you to try it. I want you to read it, do your best shot at understanding the chapters, and some of them are quite dense. And then based on that, to attempt the homework problems. And there's usually only 1 or 2 homework problems each class, but some of them are more involved. Usually it'll be one homework problem that requires either a mathematical solution or a written explanation, and one that requires some programming and simulation. I want you to try them. I'm going to grade these in a fairly unusual way, which is that I will grade the homeworks on a 1 to 5 scale on effort. I just want to see that you tried, right? And not on quality. You can get it wrong. I don't care if you get it right, but it has to be handed in before the class, and you'll get an effort grade for that. Now, then what will happen is after I give the lecture on that, you can revise your homework, and then you can hand it in before the next class, right? And at that point, you can get another 5 points, which will be on quality of the answer. Did you get it right? And what does it look like? Right? And the sum of those 2 scores gives you a number from basically 2 to 10, which is your 0 to 10, which is your score on for the total homework. If you don't have to revise it. So in other words, if prior to the first class, prior to the class that teaches about it, you turn it in and you're pretty sure you're right, you don't have to revise it, in which case I will give you your quality score based on the first version. But if you want to revise it before the second class, you can. On the other hand, if you turn it in late, so if you don't get me the homework before the first class, then you won't get an effort score at all. So you'll immediately lose 5 points. You can still turn it in before the next class to get your quality points, but you won't get the effort points. Again, this shouldn't. It's homework for every single class. You can email it to me, or actually, I think we'll be able to submit it through Canvas, and I'm going to prefer that. I apologize for putting everything in Canvas. As much as you can do in Canvas should work. If for some reason that doesn't work, email it to me. But it will timestamp it, so I'll know when these things come in. But this is the idea: is that I want you to do the reading before every class. Is very important. I want you to try and understand it, because then as I lecture, you'll have reasonable questions and you'll know what you understand and what you don't understand. It does mean you've got to be fairly involved with all of this. But the homework is a total of 20% of your grade. Like I said, there's a project that's 40%, and we will have a final exam on December 18th, which will be the other 40%. The final exam is, as with most of these Zoom exams, I haven't figured out all the details of it. It will be open book, but I do not allow collaboration. I don't want you to collaborate on the homeworks. Obviously, people talk to each other. You can discuss the topics, but I want you to do the homeworks yourself. If I think that there have been people collaborating or sharing information, I'm going to ask you about that in greater detail. Hopefully all of this is reasonably well spelled out in the syllabus, which has most of the rules as well as the lecture schedule. But of course, if you guys have questions, you can always email me. My email is on there, tsanger@uci.edu. I have several different email addresses. They all go to the same place, so don't worry about it. I have an administrative assistant. If you need to make an appointment to talk to me outside of the regular office hours, you would contact Allison Matsuoka, and she would be able to set up a particular time to meet. Everything's going to be virtual. I'm not expecting there to be anybody back on campus this quarter, so we'll be doing everything that way. In general, the lectures will be by Zoom. You will be able to ask questions when it's not taped. You'll be able to ask questions during this, and we'll probably do that either using the chat feature to write down questions or by raising your hand. And again, longer, more in-depth questions, things that are more related to your own particular homeworks, I would ask you to save for the office hours immediately afterwards. But things that would be helpful to other students in the class, then I'll ask you to bring those up, because I may miss things or go too fast, and you need me to slow down or explain something. And chances are, if there's something in my lecture you don't understand, probably some other people don't understand it either. So it will be helpful then. trying to think what else, sort of nuts and bolts. Things will come to me as we go through this. This may not be the only taped lecture. There may be a couple of other ones where I have to tape them and let you know. I will send out announcements by email to everybody, but there will be announcements in the in Canvas, so keep track of that. The assignments will be in Canvas, and when possible, please turn in your assignments through Canvas. I do ask, any assignment that includes computer programming, I will ask for a brief explanation of what you did and why it works. By brief, I mean like a paragraph or two at most. I will ask for commented code because I want to know how you did it, and I can please comment it so I can figure out what's what, but I can sort this out reasonably quickly. I'll ask for your printouts, and I want the code to be good enough that I could the code itself will replicate the outputs. So if there's data, you can embed it with the code and upload all of that. I'd like to be able to replicate these things, and that gives me a better sense. I may not do that, but if I have a question as I'm reading through it, that'll save some effort. All right, so let me see if I can get going here. Let me see if I can share my screen here and get us moving on this. Okay. So the way I'm going to try to do this is using more of a Blackboard format, and what you'll see here is that on one side of each of these, okay, it's kind of working here. I will have a picture out of Haken, and these are just the pages out of Haken. They're going to be quite small. It may be hard to read on the screen here. That's okay. You guys have a copy of Haken either electronically or not, and then you can figure out which pages these are. I'm going to go through. I'm not going to bounce around. I'm going to go through in order. My goal is that you understand everything in the book that we're covering, and we're not covering the entire book. But we'll be doing many of the chapters in the book, and again, I will have some supplementary material as we go along. So that's the introduction. I apologize for the lengthy introduction, but that was I wanted to get that information out there. Now this first chapter is an introductory chapter, and it covers much of just the overall structure of things. We're going to get into the math in more detail, and it does accelerate as the book goes along. And Haken and I will assume sort of more and more mathematical background, or we'll teach it, but there will be more and more mathematical background, including things from optimization theory, things from sort of Bellman type optimization and other forms of optimization. And information theory, statistics, and I'll teach you those things as we go along. But you'll get a sense today of the way I'm going to approach this. These lecture notes, I will be doing all sorts of markups on these lecture notes as we go. I can scribble on these things, and after the class, I will make a PDF of my marked up lecture notes available to people. I apologize in advance for my awful handwriting. However, I don't count on my notes to be comprehensive. I may do things very quickly. I may erase them after I do them. So if there's things that I say that you think are going to be important for your understanding, please write them down in your own notes. These are not some kind of definitive lecture notes for this. I might someday create formal lecture notes for this class, but I would assume that the book is actually the primary source of information for you, and that's why I'm going to go through this. Okay. So, artificial intelligence and machine learning theory. Disclaimer. Everything I say is my own personal viewpoint. It may not match other people's viewpoints. That's okay. I just want you to learn how I think, and then you can decide how you want to think. What is intelligence? So most people are aware of the Turing test, because the problem with the definition of anything is how do you measure it? And the Turing test is the idea of the Turing test is intelligence is whatever it is that humans do. And if you make an intelligent machine, your test is, can you tell that it's not a human, right? So you put a machine and a human in two rooms, and you have somebody else who can type questions to them, and these things can type answers back to you. And your goal is to figure out, are you talking to the human or are you talking to the machine? And if a human cannot tell the difference, then you say that machine is intelligent. And there's a couple of things that are very clever about this, right? Which is that the machine that is trying to be intelligent does not know in advance what it's going to be asked or how it's going to be asked, right? You could say, please compose a poem. You could say, tell me about your mother. You could say, why are mothers important? You could ask lots of different things, and the machine would have to be able to give you an answer that was indistinguishable from an answer that some human might have given you. And the reason that's important is because some aspect of what we think about as intelligence is about this incredible flexibility and breadth of applicability. And so when we talk about artificial intelligence, we're almost never really talking about that kind of intelligence. I mean, artificial intelligence that allows a car to learn to drive by watching what a human does is fine, but is not. There's no, it would be very easy to distinguish that, right? A self-driving car and a human-driven car are very different things. And it's very easy, right? All you have to do is yell at the self-driving car and nobody leans out the window and yells back at you, right? So from the point of view of the Turing test, then none of these things are going to pass, right? So that's not really the issue about this. It's not the flexibility. So we're talking about something. Intelligence is something about doing things in a very narrow field, the same way that a human might do. It's something about figuring it out. And intelligence seems like it's a bigger thing than learning. So I think that most people, when they're talking about artificial intelligence, are really talking about artificial learning. The real idea of artificial intelligence, R2-D2, who can kind of somehow figure out figure out how to get his way into the programming system on the Death Star and implement a plan that he himself has figured out based on understanding the motivations of the humans around him. That level of intelligence is not something that we're really equipped to work on at this point. That may emerge from these types of from some of the technology that we're working on today, but we're really quite far from that kind of thing. But we can do certain kinds of planning, and we can do certain kinds of learning and things that mimic some of the learning aspects. So what is learning? So that's an important thing. And there's a difference between learning and adaptation. So let me say what adaptation is. So if you, if I put a heavy weight on your wrist, right, initially you're going to sort of move slowly. You'll have trouble with that. But over time, you will adapt to it. And now your movements will become normal. And now if I take the weight off your wrist, your arm's going to feel lighter, and it's going to maybe move in abnormal ways because it feels lighter, but then after a little while, it'll go back to normal again, right? So that you adapt to things. If you're, there may be changes to the environment, you adapt to temperature, you adapt to forces on your body. If I put glasses on you that move everything in the world to the left, you'll bump into things for about 10 minutes and then you'll figure it out and then you won't bump into things anymore. And then you take the glasses off and now you'll bump into things again because the world is now shifted to the right as far as you know. And then you won't, and then you'll readapt, right? You'll adapt and de-adapt. So adaptation is sort of a temporary adjustment to things in the world. And that can be very important. You could be measuring background noise and trying to cancel it out. You could be trying to figure out, can identify the voice of one speaker among many people captured on the same microphone. These are all types of problems that could be done in adaptation. I mean, that speaker's voice could change over time. Learning is permanent. You can't unlearn. Learning means essentially and this is there's a couple of different definitions, but I'm using the one from Richard Schmidt. And Richard Schmidt had this definition, and again, I really have to apologize for my handwriting, made worse by the fact this is all electronic. But the idea is learning is permanent. You can't unlearn. Once you know, learning is like, how do you ride a bicycle? So now I know how to ride a bicycle. Could I get worse if I don't practice for a while? Sure. But I'm never going to forget, right? You can forget facts. I could tell you, the Nile is the longest river in Africa. And then I could come back to you a couple of years later and say, what's the longest river in Africa? And you might not know, right? But if I teach you a skill, you learn, what do cats look like? How do you ride a bicycle? How do you walk? No matter what I do to you, you're going to come back to how do you drive a car? I could put you in a different car and maybe it would drive, you'd have a little trouble. You'd have to adapt to it, right? And then you go back to your original car and you might have to adapt back to that original car. But you don't forget how to drive. So there's a fundamental difference between learning and adaptation. And again, these terms become very important because when we start looking at networks, I want people to be accurate about how you're using these words. So again, to be clear about this, learning is permanent. Learning is you learn how to do something. It's not going away. It's you can't unsee things. You can't erase ability. But adaptation is a change in your response to a temporary change in the environment as you need to be able to move in different environments. Okay, so now where does this now to sort of come back to some other definitional issues here? Neural networks, where did this come from? Obviously, there's a lot of people who want to know how the brain works. The reason we want to know how the brain works is the only thing that so far can pass the Turing test is another human, right? So if I put two humans in a room, yes, you cannot distinguish that you can't figure out which one is human because they're both human. And of course, now people may answer questions differently. But if you think about it, humans pass the Turing test, right? And we're just machines. So at least there's one extant example of a machine that is capable of passing the Turing test, and that machine is built out of neurons. And the thing that is fascinating about this is that we think of neurons as very noisy, slow, inaccurate things that are sort of connected in semi-random ways to other neurons. And yet, this little 15-watt piece of machinery with its 100 billion neurons and 10 trillion connections and so forth, has the computational power that's probably equivalent to or greater than the entire internet at the moment, and certainly can solve certain types of problems that can't be solved in any other way. We have a tremendous amount of memory. I mean, you can, over a period of 3 days, look at 10,000 different images and store information about those 10,000 images, seeing each one for just a second. I mean, the storage potential of this thing is unbelievable. You have, if you do basic calculations on some of the storage capability, you have enough memory in parts of your brain to record hundreds or thousands of pieces of information for every second of your entire life. You can literally record a video at a kilohertz of your entire life and have access to that. You can't recall it, but it's in there at that level of timing. So again, this is a very, very powerful machine and running on 15 watts of power. So wouldn't you like to know how to build one, right? And so a lot of this was really inspired from that, sort of looking at neural structures and saying, is there something about these that can teach us how to do computation? Maybe we could figure it out some other way. There's no strong reason to believe that that's the only way to do it. You don't have to use these structures. There may be perfectly good other ways. Again, von Neumann architectures solve certain problems that humans aren't very good at solving. Large numbers of mathematical operations can be done very, very fast with complete accuracy at relatively low power and with high levels of reproducibility. It's just we can't do the things humans do. We can't categorize. We can't learn at the same kind of speed. For instance, machine learning, typically, if you look at the kind of things that Google will do in machine learning, they say, we have all these huge data sets. So I can give 1 million examples of cats to a network, and then it will learn what a cat is. That's fine. But a human, I just need one example. Here's a cat. The next time they see it, oh, that looks like a cat, right? I mean, it's just the kind of learning that's done is very, very different. So obviously there's some value to studying this, and that has led to a lot of the inspiration. It's not the only thing. There's a lot of the algorithms we're going to talk about are only loosely inspired by neural systems, but these were called neural networks. Then it was changed to the idea of connectionism, because one of the characteristic features of the biological computation is information is stored in the connections between neurons. So if you look at what a neuron looks like, this is a typical neuron this appears to be a description of a pyramidal cell from cortex, certain motor areas of cortex. And as you know, there are, as a cell body, and information comes in from dendrites. And the brain is set up in layers so that what will happen is that there will be these things will be in layers. The cell bodies will be in one particular layer, and it will obviously communicate with other cell bodies in that layer. And then there will be there's other layers up here, and each of these layers has different kinds of inputs and outputs. And so there may be connections within layers, but There may be things that come in from these places. There's things that come out from different layers that are a little bit deeper down. So each layer has intra-layer processing and sends information back and forth to the other layers. Some are primarily input, some are primarily output. So you have this idea that neurons they take information from one place, they send it somewhere else, but all the computation is basically being done by transmission of information. There's no arithmetic logic unit. There's no Boolean processor here. Yes, they can probably do Boolean operations, but it looks like much of the structure is really about passing information from one place to another. Now, there's a lot of stuff that goes on in these dendrites, they can be modulated in many different ways, and the things that come in can be modulated, and there can be feedback, so you can have an incoming signal, there can be feedback on the incoming signal. These things are modulated by neurotransmitters, which can bathe the entire thing or be released in small areas. So there's a lot of pieces to this, and I can tell you from a neurologist's point of view, you can't break any of them. It's delicate in the sense that if any one piece of the algorithm is broken, the whole thing fails. But it's very robust in the sense that I can take out an entire chunk of this, everything in that chunk, but as long as most of the pieces remain in other chunks, the whole thing will work. That's very different. I mean, there's probably no single transistor I can remove from the CPU of a modern computer without making the thing just stop. It will start to not only generate errors, it will probably just stop catastrophically, so that you need very high levels of reliability in silicon computational systems, whereas in a biological system, of course, you have this type of reliability. But I cannot remove one receptor. So if I remove all the glutamate receptors or all the GABA receptors, the whole thing fails. So they're robust to spatially localized injury, but they're not robust to computationally localized injury, which you imagine makes sense, right? I mean, these computations are very important. And if you're missing a neurotransmitter or receptor, that will affect very, very large regions of brain. So one of the things that is an interesting way to think about this is based on David Marr. And David Marr divided computation into basically three levels. There's the overall computation. What are you trying to do? I'm trying to do object recognition. I'm trying to drive a car. I'm trying to create a walking robot. And what are the features of driving or walking that are important? You know, the locomotion, alternating your legs, maintaining balance, visual targets, navigation. These are the features of the computation required. And then you can look at, and that's at the computational level. The next thing you look at is the algorithmic level. So in the algorithmic, well, what are the algorithms I'm using for this? Like, okay, I'm going to use reinforcement learning to plan my path. I'm going to use a supervised learning algorithm to learn the forward dynamics. I'm going to use another supervised learning algorithm, maybe with backpropagation through time, to learn the inverse dynamics. And so I'm going to use these specific algorithms to learn the pieces that are necessary to accomplish the overall computation. And then you have the implementation. Well, how did I build it? What's it made of? Is this made of silicon? Is this done on a GPU? Is it done on a other type of parallel architecture? Is it done on a very fast serial architecture? Is it mixed? Is it done on a neural architecture? Is it done on a simulation of a neural architecture? So those are the implementations of these things. And it's important to realize that, because you can implement a multiplier in neurons. It may not be a very good one. It may be inefficient, use a lot of power and make errors, but you can still build a multiplier out of things that look like neurons. And one of the things that we're trying to do is build a brain out of something that looks like silicon. And we can simulate things. So you can emulate within your implementation layer. You have the ability to emulate using different implementations, different kinds of algorithms. And of course, that's how we test this, right? We can emulate a neural algorithm. We can even emulate a neural implementation using a silicon-based algorithm or a von Neumann architecture. So those are, so again, thinking about these levels is often very helpful in recognizing that there's a lot of flexibility, and that explains the way these algorithms often get used. And in fact, even when we talk about these implementations, there's many different kinds of neurons. If you can, so if the implementation of neurons could be at the level of synapses or chemicals or membranes. I mean, there's lots of, or you could do it at a very mathematical level. And I'm going to talk here at this very mathematical level. So here's a very different image of a neuron, right? So we start out with this thing, and now we end up with this thing. So what is this? The idea that the neuron is, okay, we think that dendrites take lots of inputs, and somehow we combine all those inputs at the cell body, and then we send something out on an axon, right? So these are the dendrites. Excuse me, these are the dendrites, and this is the axon going out, right? And then here I've got a cell body. So what happens with this is that we have so what's the simplest possible model of combining things at the cell body? So maybe the simplest possible model here is we're just going to sum all our inputs. So that's a summation sign. And then we're going to have, and each input is just a number. And these are these numbers, which we're going to typically call X. But the synapses come in, they have different synaptic strengths. There really isn't a different synaptic strength. Every synapse is exactly the same strength. If you depolarize a synapse, you get an excitatory postsynaptic potential or an inhibitory postsynaptic potential, and they're pretty typical, they're about the same. But what happens is that when an axon comes in, it can branch. Oh, see if I got this right. It can branch, the same axon can branch in lots of ways. So this axon coming into a dendrite is going to have twice the power of this axon coming into a dendrite. So there's some ability to do that. And then these synapses themselves can be different sizes and release different numbers of vesicles. And where you are on the dendrite makes a difference. So if you excite further out on the dendrite, it's a little bit harder for that signal to make it all the way to the cell body than if you excite in here. And then there's all sorts of weird nonlinearities. So if I excite this before that, it may block the things coming down because the signals have to transmit along the dendrites to get to the cell body. So we're back here, right? A signal that comes in up here has to transmit along this dendrite all the way down to the cell body. If somebody else came in here, it could potentially block that. So that there are all sorts of nonlinear things that could happen that are not in this model at all. This model just says we've got a signal that comes in. There's a certain strength on that signal, which we'll call X1. There's a weight, W1, which describes how easy is it for that X1 signal to get through to the dendrite. And then we just simply add everything up with a straight addition to generate some kind of an output. And then we say there's some kind of an activation function at the output, because what we're talking about here, these X's, what are they really? The signals in the brain are carried on spikes. So the signal coming in really looks like, there's a spike and maybe a few more spikes. And there's the idea that in this range, this is sort of a low signal because the spikes are not firing very fast. And in this range, that's a high signal because there's more spikes firing. So sort of a firing frequency, or in any brief period of time, we could think of a firing probability. So this area has a higher firing probability than that one during that time. And that's based, and again, we're not going to talk much about spike theory, but the point is to recognize that the actual signals in the brain are carried as spikes that are being sent along axons. A spike is a depolarization event. It's a very efficient way to transmit information along axons. And those spikes, the probability of a spike firing, the higher the probability, the more spikes you'll get. And the more spikes you get, the more chances are that you will depolarize or transmit a signal to the receiving dendrite. So that means that these X signals behave like a probability of firing in a small time interval. So those probabilities of firing are real numbers, right? It's not, again, if you look at this structure, these X's are real numbers. They're not spikes. They could be a spike count. You could say, okay, how many spikes occurred in the last second? So if it was 100, I'm going to call X 100. If it was 20, I'm going to call X 20, right? But the problem there is you have to wait a whole second and count spikes. So what you really want to use is, instead of waiting the time and counting spikes, you're going to say these X's represent the probability of a spike in a small time interval, whatever that is. So if you were firing at 100 spikes per second, at the level of a millisecond, you could say, okay, I've got about there's a chance of one spike about every 10 milliseconds. So there's about a 0.1 probability per millisecond of a spike. And so we're going to say that that's 0.1. And these become, so it's a probability per unit time. And of course, probabilities have a range. They can only be between 0 and 1, right? So all probabilities are between 0 and 1. And now when you send the output here, again, the output is a spike, right? It either fired or it didn't. But the more inputs there are, the more there's going to be a higher rate on the output. So again, the output is going to have a firing rate. And again, that firing rate on the output should be a number between 0 and 1 because it's a probability of firing within whatever interval delta t you're talking about. Okay? And again, this is not strongly covered in Haken, but I just want to give some idea of what this is. So recognizing that, what people sort of say is, look, we could deal with these firing probabilities, or we could deal with spikes and all of that, but we don't really have to. Let's just say these are real numbers. Let's take the simple model where the x's are real numbers, maybe between 0 and 1, or maybe not. You know, maybe these are just the pixel values coming in, a number from, 0 to 255 on an 8-bit pixel or something. It doesn't matter, right? Because we can, whatever this range is, we can always compensate for it in the weights. You know, if instead of being 0 to 1 is 0 to 255, okay, so the weight is whatever it would have been divided by 255, right? So it's so we can compensate there. So it doesn't really matter that much. And the same thing for the output. It could just be a real number. It could be between 0 and 1 or not. And again, when we think about that, what we're doing is we're talking back here at this implementation level. So we're saying, okay, we're going to come up with something that has this feature of neurons, which is where the information, the stuff that's learned, is in the weights, and that they communicate with each other. But the actual signals that are being communicated are real numbers being passed around. And I'll come back to later why that has both good and bad things associated with it. But a lot of the models that we look at, and many of the models, most of the models in this book, sort of assume that we can pass real numbers around. But neurons don't have real numbers. They don't have access to that. All they can do is fire spikes, and they can fire them at different rates and different patterns. Which has there's some real beneficial things to that. If you cared a lot about disease, the implementation level matters because, of course, different implementations will break in different ways. So then it becomes important. But if you care about how does the implementation support the algorithm, then perhaps it doesn't matter quite so much because all the implementations are supporting the same algorithm. And that's what's going on here. So we want to talk about an algorithm that primarily looks at communication. And this is basically the algorithm. So now we've taken this whole complex idea of spikes and spike timing and postsynaptic potentials and membranes, and we boil it down to a very simple kind of equation, which looks like this. And what this says is that we have the inputs X and we have the weights W. And so each input has a synaptic weight W. The cell body sums all of that up. It runs it through a nonlinear function H, or not, doesn't have to be nonlinear, but you could. And that produces some output Y. And the X's and the Y's, these are just real numbers, as are the W's. These are just all real numbers, right? And H is a real valued scalar function, right? So now we can, Haken talks a lot about the idea that you add a constant offset there. That's fine. There's another way to add a constant offset, which is just we're just going to set x0 equal 1 and w0 times x0 equals w0, and we're just going to call that b. So the point is that you could add this b in there, or you could just pretend that there's a constant input, and it's equivalent. And from the terminology point of view, I'm generally going to use vector notation. So if X is a vector, W is a vector, and I'm going to assume that vectors are column vectors. So W transpose X accomplishes this summation. That's just the dot product. W dot X equals W transpose X, right? It's the dot product. And that dot product will give you, again, this structure. So the structure here is the W dot X summation. And that structure there becomes gives you the W transpose X, and then this is now a scalar. This is scalar, and then that scalar function we run through the nonlinearity H to produce the output Y. Okay? So that's the basic structure of the simplest form of neural net, and remarkably, this thing is incredibly powerful. So nowadays, one of the most common forms of the H function that is used is the rectified nonlinear unit, which looks like this. Okay, so this is H of, let's call it H of U, and this is U, right? And you have this rectified nonlinear unit. And so that's, this 0 point becomes very important. And typically what will happen is that's what this B value will control where that 0 point goes, right? So you know, the nonlinearity is applied to W transpose X plus B, and the B creates an offset there, right? So that if you think about it, these things become very important. Haken doesn't talk as much about the rectified linear units because that's become much more commonly used with Hinton's deep learning frameworks, and previously was not used all that much. The problem with the rectified linear units from a theoretic point of view is that there's no upper bound. So these things can have arbitrary outputs. The advantage of them is that they're relatively simple to do certain kinds of computations with. Note that they are not differentiable at the hinge point. And so certain types of algorithms don't do very well with that, or you have to do clever things to get around that. But one of the things that typically does happen with these things is that, so one of the things that people were very interested in initially is in not having that unbounded, this rectified nonlinear unit. So you could imagine coming up with something else. You could imagine having something that went like that, went like that, and went like this. So now it has some kind of bound, and typically you'd say it was between 1 and 0. Again, if you thought of these as a probability of firing, you might want something that was bounded between 1 and 0. But it could be bounded. It represents the fact that all neurons have a maximum firing rate. Most neurons can't fire more than 200 or 300 spikes per second. They can't fire less than 0 spikes per second. So if these numbers are supposed to represent the firing rate of a neuron, it would be good if they were bounded in some way. And then it's nice if they're differentiable. And so then people would say, okay, well, let's make things that look a bit smooth like that. And this is what's called a sigmoid, because sigmoid sounds like S and looks a little bit like an S. That is the, so now we have these sigmoid curves. So these things are rectified linear units, which people write as ReLU units. We have sigmoid units, and this is just a bounded linear unit. Okay. Now, so there's a lot of question when we get to information theory. There's going to be a lot of tricky things, but this idea of what is the maximum transmittable information is an important piece of information. And I just want to throw this out there now because I'll come back to this at various points and we'll discuss it in greater detail in the information theory lectures. But if I want to ask how much information can I transmit? So suppose I have a bunch of input units and I've got a bunch of output units, right? And I can kind of transmit information through all of these, right? Now you would think that this would have more information throughput through this than just a single unit, right? It should be more because you have more inputs and you have more outputs. And so I should be able to have, but the fact of the matter is that's not true, because a real number, imagine what the binary representation of a real number is, right? What's the point of a real number? You know, there are things like, you know, let's think of what they might be. Pi, you know, 1/3, sorry, I want non-rational numbers. So I actually don't want to use 1/3, but things like pi, e, things like that. Numbers that kind of go on forever, right? And the interesting thing, as you know, about numbers like pi and e is not only to go on forever, the sequence never repeats, right? And so you can make real numbers that have that. If I have any arbitrary bit string, let's take all the data stored in the internet everywhere, coded as a bunch of 1s and 0s, everything in your computer, a bunch of 1s and 0s, and it's going to go on for a very long time, right? But that I could represent that as a number, right? Just as, you know, a binary real number looks like, you know, 1.0110000111110. And that's a perfectly valid binary representation of a real number, right? And I could call this number X, whatever number that is, right? So now I've just taken the entire world knowledge and represented it in a single real number, right? So real numbers have unbounded information content. So there's actually the information transmittable in this network and transmittable in this network is the same, right? So if you allow for real numbers to be used. Now, there's no real numbers because everything either has noise, is quantized in some way. So this isn't a real problem in the real world, but it's a theoretical problem. We do have to be careful about that. So you have to, and you'll see that in all cases, there's going to be something about the algorithm that makes real numbers kind of not behave like real numbers. For one thing, you have to be able to extract the information. If I represent a number, a real number like this, and I want to extract information from it, it's just like reading a tape, but it might take me a long time. I might need to read along that tape for a very long time before I get to what I need to get to. But that's fine. It's only finite, right? There's only a finite number of bits on the internet. So in fact, it's not a real number. It's a rational number. It will terminate at some point. But no matter how much is there, you could always represent more of it. But you do have to know where it is within that tape, and you have to be able to find it and index it. But you could, right? I mean, your disk drive is just a sequence of bits, and those bits could be represented as a single real number, or again in a disk drive, because it's finite, it's a single rational number, right? Just anyway, it's important keeping that in mind, and we'll come back to this more. So now let me get back to these ideas of these sigmoid functions, where the sigmoid functions are actually very interesting, and again, throughout this, I'm going to make links back to standard statistics. There's many ways to represent a sigmoid function. One of the ones people use is the hyperbolic tangent, has a sigmoid type property to it, and there's lots of ways to do this. So the arctangent has a sigmoid property to it, looks vaguely sigmoid, and you could just the integral of a Gaussian, right? If I take a Gaussian and draw a Gaussian like that, and I integrate that, I'm going to get a function that goes from 0 up to 1, right? The integral of any probability density is a probability distribution which always integrates to 1, from 0 to 1, right? So any probability density will give you things like this, and anything that looks smooth is going to end up looking sigmoid like that. So you already begin to get the sense that there's something special about sigmoid functions, because the derivatives of sigmoid functions tend to look like they tend to sort of look like one-lobed probability densities. But this is one particular type of sigmoid function, and this one is very classic, and was used for many years. And it's 1 over 1 plus the exponential of W transpose X, right? So this is your linear input, and then it goes through this nonlinearity. That term A determines how sharp this is. So here, as you increase A, you get sharper and sharper versions of this. In fact, until you can get, when A becomes infinite, you get something that looks like a binary switch, right? It will just go from 0 to 1, and there's there's nothing in between, right? But it's differentiable for all finite values of A, and that's nice, because you will see later it's important to be able to differentiate. But these are binary. A binary unit looks like this, and the point is these sigmoid functions will converge to binary units as you go to higher and higher gains. And so the limit as A goes to infinity of sigma of W transpose X basically is a threshold nonlinearity, or the binary nonlinearity. And if you put a binary nonlinearity there, then that was the original model of McCulloch and Pitts, originally proposed in 1943. So this stuff goes back a long way, right? And we know a lot more about neurons since then, but surprisingly, much of the modeling hasn't changed nearly as much. Now, looking at this particular function, this function has some interesting properties. There's this concept in statistics of what's called a logit function. And the logit function is this thing, log of p over 1 minus p, where p is a probability of something. Now, why do we do that? What does this actually do? We call that logit p. But there's something, when you do what's called a logistic regression. Suppose that you are trying to do a regression where you have an output that's a probability, but an input that is linear, okay? So P, and you're trying to somehow regress a probability on W transpose X. And you're trying to say, I have a linear function of the input, a linear function of some measurement, but I want that thing to predict the probability. So for instance, I'm going to take a linear function of height, and I use that as the probability that this particular blood pressure medicine is going to help you, right? So the problem is a linear function can go negative, very big positive numbers is they're not limited to being between 0 and 1 in any meaningful way, right? And so it's hard to do these regressions. You can do it, but it doesn't work out very well, and the mathematics don't work very well. So what you tend to do instead is you do this. You take the logit transform of p. Now, if you look at what this function, this logistic function does, log of p over 1 minus p, when p is 0, the log of 0 is negative infinity. When p is 1, it's the log of 1 over 0, which is positive infinity. So this takes the 0 to 1 and maps it into negative infinity to positive infinity, right? And now, which is the same range as a linear function, right? Because x could run 0, negative infinity to positive infinity. So it kind of spreads it out. It spreads out probability over a much larger range, and it allows you to do these regressions. And typically in statistical software, you will do a logistic regression in the following way. So if you are trying to predict the probability of an outcome of a clinical trial using some linear function on the inputs, you'll do a linear regression of the logistic function of p against the variable of interest. But let's look at now what this logistic function looks like. So now let's take this and we'll just try to invert it. Let's just solve for p, right? So you can solve for p. We take the anti-log, take the exponent of both sides. P over 1 minus p here is equal to e to the negative. We just exponentiate that. We can carry the 1 minus p over to the other side, and by the time you're done, you end up with this equation, which you will notice is the same as that equation. Okay. So the sigmoid nonlinearity, that's the standard sigmoid nonlinearity, is the inverse of the logistic function. And that actually has a very interesting point, because remember I said that we were talking about neural rates as representing probabilities of firing. So to some extent, what you're doing here is where the logistic function converts a probability into a rate. This function goes the other way around. It's essentially converting a rate into a probability. So this incoming rate, W transpose X, is converted into a probability of firing at the output. And which makes sense, because the output now runs between, you have a range from 0 to 1, which is a probability. So these logistic functions create probabilities. Again, the rectified linear units don't do that. They have interesting computational properties, but they don't have this interpretation. And we'll come back to this when we get to the next chapter, but really thinking about these nonlinearities really do change the properties, both the mathematical properties as well as sort of your ability to interpret what these things mean, as well as just the function of these networks, like how well do they work. And so when you're trying to do networks that are going to predict probabilities of things, you may want to use nonlinearities that map linear things into probabilities. Again, I'm going to come back to all of this, but I do want you to start thinking about this in this particular way. Excuse me. Okay. So let me move on here. The book, I'm not going to do much about this, but the book you'll see uses this this sort of diagram as an alternative way of looking at these things, as combining things at nodes. That's fine. You can use any way of drawing this that makes sense to you. Now, you talk about two-layer networks. Again, these are more terminology things. When you talk about layer networks like this, each one of these, if you just look at this piece of the network here, that's the thing we were already talking about. But now we have another piece like that, and we have another piece here. So now we have all of these. This is like 4 networks in one. And so how do we do that? Well, now we have 4 outputs, right? So there's 4 outputs, and maybe there's, in this case, there were 4 inputs. And now we write it like that. But of course, now you can just write the thing as a matrix operation, right? And so this W matrix looks like this. For each, the way the WJ transpose X, so we're multiplying times X here, right? So this is W0, Wn, and this thing is, so let's put Wx there, Y equals Wx, and Y looks like this. So this is Y. So that's y0 to yn. So what happens is each row of this matrix multiplies by x and produces its corresponding output. Okay? And so these are sort of the outputs of that. And then you can ask, okay, what would happen if I took this matrix and I were to put in a x, which is 1 and a whole bunch of zeros, right? Now, what's that going to do? That's going to select the first column here. So the first column of this matrix is the effect on y of the first input. The second column is the effect on y of the second input, and so on. And the first row is the way that y is computed, is the effect of each of the inputs on the first output. And you've probably all seen this in linear algebra, but again, I just want to remind you of what matrix multiplication looks like, what these structures are, right? So the rows tell you the weighting of each input on each output, and the columns tell you the effect of each input on all the outputs. Okay. And I will use this terminology quite commonly. Now, networks can get more complicated. So now we can have, this is a more typical network, and now each of these units may have a nonlinearity in it, right? It could be a rectified linear one, it could be a sigmoid nonlinearity on it, but each of these has little nonlinearities on it. And so this thing here becomes these are the hidden units, these are your output units, and these are your inputs. So now if you're going to write out what the structure of this is, the output here is you may have, let's call this x, call that u, and we'll call this y. So u j is equal to some sigmoid function, sigmoid function of some set of weights, wj transpose x, right? And we might typically write that instead as saying u is equal to sigma of wx, recognizing that we apply sigma to each x separately, as we call a memoryless transform. Right, this nonlinearity, although it has access to all of the whole vector of u's, really it just applies to each one at a time. And so that is the vector of u, and then y here might be, now y might equal, v transpose times u, right, where these weights here are the v's, these weights here are the w's, right? And that would be a very typical two-layer network. And you might have another one, or y might have, there might be a different, or even the same sigmoid function around that if you wanted nonlinearity at the output. But this basic two-layer structure is quite powerful. In fact, you can show, depending on sigma, for certain types of sigma, you can show that this is a universal approximator in the sense that for any function f of x, I can approximate, and suppose I take some function f of x and I make my best approximation using this network y of x, and I figure out what's the squared different distance between those. I can make that arbitrary small, right? So for any epsilon, I can find a network size that is sufficient to make this. For any epsilon, there exists an n number of hidden units such that the error is less than epsilon. And that has been rigorously proven for certain classes of nonlinearities. And we'll talk about that. Particularly, this happens in radial basis functions. But these three-layer networks are very powerful approximators. It doesn't mean they're efficient approximators. N might be 100,000 to compute a very simple polynomial, and so that's not an efficient way to do it. But you can do it, right? And one of my favorite sayings is, if you have a powerful enough motor, a square wheel will work. And a lot of the networks that we use are effectively square wheels, and we now have enough data and enough computing power that we don't have to worry about whether they're efficient or not. But if we're really going to try to mimic human intelligence, efficiency still matters. And so again, we'll get to the point, and I hope through this class you'll begin to understand how you can choose the nonlinearities in ways that can make much smaller, more efficient networks that are just as good approximators as large ones. There are some other types of network structures, or, well, let me put it different. So this is a very typical network structure. Now the question comes up, what could we use networks to do? Okay, there are, they can be hooked up in lots of different ways. When there's dynamics involved, you could take the output of a network and you could make it the input at the next cycle, right? I could say, I'm always going from x at time t to x at time t plus 1, right? And so to get from x at time t plus 1 back to xt, you need a time delay, and these are delay operators. And you notice these delay operators, people use this term z inverse for that. For those of you who remember what Z transforms are, you know that Z inverse is essentially a delay operator. I put the proof of that here, but it's fairly straightforward. But essentially, we use it just as a terminological thing. I mean, Z inverse, think of it as a delay operator. But in fact, if you took the Z transform of a discretely sampled signal, it is a delay operator. So when you multiply a Z transform of some signal x times Z inverse, you essentially get the Z transform of x t minus 1. Right? So it operates in the transform domain as a delay. Again, I'm not going to go over that. It's just more, I just wanted for people who are wondering why is Z inverse used to represent a delay. You'll see that. But recurrent nets can be used to learn and implement dynamics, right? So if I want to implement this as a standard dynamics equation, xt plus 1, so a much more typical dynamics equation might be xt plus 1 equals a times xt, right? That's a very simple sort of dynamics for a linear system dynamics. So here I can implement a nonlinear system dynamics just because I put the sigmoid function on it, but it's still implementing dynamics. And you could use it to emulate dynamics, to predict them, or to create dynamics that you want to create. This is the same kind of thing, but now with, instead of a very simple network like that, we have a more complicated 2-layer network that can be 3 layers of networks, and these things can again create or mimic different types of dynamics. One of the problems that we will have with all of these multi-layer networks is how do you find the hidden units? And what I mean by that is either how do you find the, and I apologize, I swapped the variable names here. How do you find the V's that become the hidden? So here's X, here's V to these guys. I'm now going to run through sigma, my sigma box. I'm going to run through W, and I'm going to get to some output Y, right? So but the point is, these are the hidden units. This is easy. Once I know the hidden units, if I have the right hidden units, finding the linear thing, finding a linear relationship between these hidden units, let's call them U and Y, that's easy, right? That's just this can all be found by a linear regression. But how do you get the hidden units? So that becomes the topic of lots of things. That's what backpropagation comes from, but there's lots of other ways. Backpropagation is only one way in which you can find hidden units. But this becomes fairly critical. One of the reasons it's critical, and Haykin talks about this, is this idea of knowledge representation. And the hidden units are the representation, an intermediate representation of knowledge that is then going to be used to do something. So if you think about it, you started out with X, which is your input, and maybe that's your retina, right? Maybe that's vision that comes in, and now you're going to map it onto something else non-linearly, which might be edge detectors or bar detectors or motion detectors or color detectors, but you're mapping it onto a different space, which is your internal representation of the raw external data. And it turns out that that representation is very, very important. If you get it right, then this last layer is easy. If you get it wrong, the last layer is very hard, right? If you are trying to represent the set of all cats by a representation that counts the amount of hair on them, it may not be particularly helpful. In fact, even color is probably not particularly helpful. But things like faces and tails and legs and fur would be a very helpful representation. So certain representations, it's not that you can't solve it with a bad representation. It's just not going to be very good. And so you want to get these things right. So one of the things that representations try to do is they can help you with categorization. So if you have, let's suppose that you have images of, I'm clearly a cat person. Suppose you have images of 2 different cats, right? And, or even the same cat, right? And they're shot using a camera that has different lighting conditions, right? The white balance is off, or the exposure is different on the 2 pictures, right? Exposure doesn't matter. Whether the room is well lit or not well lit, or the direction the sun is hitting them, or the background, or what they're standing in front of, none of that matters. But how do you know that, right? How does a network know that? I give it 2 pictures, say, these are just 10 pictures of cats, here's 10 pictures of dogs. It turns out all the cats were standing on grass and all the dogs were standing on sand at the time. So what does the network know from how to distinguish the cats from the dogs? Oh, if it's on grass, it's a cat. If it's on sand, it's a dog. Well, that's true, but it won't have learned what you want it to learn, right? It will have learned the wrong thing. So what you want to say there is the background doesn't matter. What we're trying to do is find four-legged things with heads and tails, and those are the features that matter, right? And the shape of the legs, the shape of the head, the shape of the body, the size, those are the things that matter. So if you represent it correctly, you can make the distinction. Now you want these things to be similar. You want all dogs to kind of come out with a similar sort of representation. Right? And in fact, you would like them to be more similar than the representation for all the cats, or for all the orangutans, or all the trees, or something like that. So one of the things that Haykin is pointing out is you want similar inputs should produce similar representations inside the network and should be classified as belonging to the same class. Now, one of the things that I would like to point out is that when similar inputs cause similar outputs, we call that smoothness. Smoothness by itself doesn't help you as much as you'd think for these classifications. What you really want is when similar inputs cause identical outputs. That's data reduction, but that forces the classification. So if all cats, if you show pictures of cats, right, and all cats end up with the same output, for instance, the word cat, you're done, right? So you don't care what color they are or what size they are. They've all been reduced to the word cat, and all dogs are reduced to the word dog. That's a huge reduction in information because you went from pictures down to a single word, right? So that's a huge reduction in information. But similar inputs giving identical outputs forces a categorization. Similar inputs giving similar outputs may allow you to cluster things, but doesn't force a categorization. But what it does allow you to do is to say, okay, wait a minute. These two things are both cats, but they're different cats. Once I say picture A is a cat and picture B is a cat, and I remove all other information, you say, well, which one was bigger? So I don't know, they're both cats, right? That's the only information I have. But or which one was standing on grass, right? So you could, there is other information there, so you may not want to get rid of it. But just pointing out, I wanted to point out this idea that this idea of similar inputs to similar outputs is not the same thing as similar inputs to identical outputs. But a lot of what you're trying to do with this knowledge representation is decide what you don't care about. You're trying to discard dimensions that you don't care about. Similarity is what's called a distance metric, and Haykin talks about that. If I've got a space of different points, every point in the space represents a picture, and I want to say, okay, all the cats are here and all the dogs are there. It's fairly easy. If I see a point and it lives within the dog region, I say that's a dog. If it lives in the cat region, I say it's a cat. It lives outside, I say I don't know. So either I can't tell, or it's not a dog or a cat, it's something else, right? So, but I could have chosen a different metric for that same thing, right? I could squash one, and so that all the points are living very squashed like this, right? And in that case, it's still okay because all the cats will live up here and all the dogs will live down there, right? But suppose I squash it the other way. And in fact, I could squash it sort of this way. So suppose I squash it in such a way that all the points live like this, right? And all I've done, I'm just transforming the space. I'm just doing linear, if I've got X, these are 2 dimensions here. Come on. Oh, lost my pen here. Let me get the pen back on. If this is the X1 dimension and that's the X2 dimension, all I'm doing is I'm just transforming them, right? It's not a big deal. I could take those dimensions. I don't know what they are. It could be color, it could be size, but I could do some linear transform. But if I do a linear transform like this, where all the points end up there, now all the dogs are here and all the cats are there, and I can't tell them apart anymore. So if you get the transformation wrong, it can be very hard to tell these things apart. So you want to have a representation that allows your later classification to work better. So your goal, ignore irrelevant things, emphasize differences that we care about. When we look at support vector machines, we're going to look at this in a great bit more detail as to where that comes from. The thing that you need to know is you need to know what the observer is, because what does it mean to emphasize something? Maybe the observer is very good at separating these things, and maybe the observer is very bad at this kind of stuff. Who knows? It depends on what it is that makes two things different is in the eye of the beholder. That just means that, and what I mean here is that if you're building your first layer of a network, you need to know what this layer is capable of in order to decide what the optimal solution is at the hidden units. If this layer is an intelligent, arbitrarily capable thing, you don't need hidden units at all. You might as well just pass on the basic stuff underneath it, right? If this layer is just linear, you'd better pass on things that allow linear separability. If this layer allows certain kinds of nonlinear functions, you should pass on something that lives within the space of the nonlinear functions it can do. So the choice of the hidden unit representation depends on knowing what the layer above is capable of doing. Okay, and again, remember, a single real number contains infinite information. So if the layer above, if this is arbitrarily powerful, I could just encode all of this into a single real number and pass it on there, and that's very efficient for data transmission. Right? So the power, the strength of the layer above, and ultimately its learning abilities are going to determine what's the best representation here. And I should point out in that context as well, a representation that's good for computation is not necessarily the best representation for learning. Sometimes there are things that are easy to compute and hard to learn. There are things that are hard to compute and easy to learn. Right? So it's the point is that representation you may have to decide what makes that best. And again, we'll talk about this in lots more detail. But the Haykin does talk about this idea of the distance metric. How far are these things apart? Here, obviously, they're very close. Here, they're very far. So the distance metric, which says, the metric is basically talks about this layer. It says, what does it mean to be far apart? I want to separate things as far apart as possible if they're different, and I might want to make them as close as possible if they're the same. But what that means is it's this layer that determines if they're far apart, that's easy for me. If they're close, that's hard for me. And what it means to be far apart or different may be different in different worlds, right? It's if I have a microscope, two things that are a micron apart may appear very far apart. But if I don't have a microscope, two things that are micron apart are indistinguishable. So what the distance depends, that the metric is determined by the observer or by the higher level of the network. One of the things that Haykin talks about is the idea that things with higher importance should have larger numbers of neurons. But what constitutes a large number? We'll talk about that, but it's the same issue. It depends on the observer. How many neurons you need depends on the statistics, your ability to read information out from these things. He talks about incorporating prior knowledge into things. That's important. That's sort of a nature versus nurture argument. What is prior? If you know something, why teach a network something that you already know? Well, sometimes, even if you know it, it's hard to encode it in the network, right? So I know what cats are, but how do I get that into this structure of network, right? So sometimes, even when you have prior knowledge, you're better off teaching it. But prior knowledge of things like, that's poisonous, I'm going to make it taste bad, is one of those things that is often built into systems. On the other hand, that doesn't explain things like blue cheese and Brussels sprouts, right? I mean, there are things that most children find relatively distasteful, but that actually adults can learn to like. So, or spicy foods, right? There are things that ought to be painful, but the people discover they like. So a lot of these things can be changed with learning, but we do come in with some presuppositions which probably are useful for survival. But how do you encode prior knowledge? Well, that can be about what's important. And again, this can come down to the metrics used that say what does it mean to be far apart or close together in space? Those things represent prior knowledge about the observer, about the second layer of the network, the thing that's going to use the data, where we're handing it off to. It's always, so you always have this input layer. There's a layer of hidden neurons where you're encoding what and you can learn these things, a layer of output neurons. These can be learned or these can be fixed. Radial basis functions, those are fixed. And that's because we know something about encodings in a wavelet decomposition or a Fourier transform or a Taylor series. I will explain why those are hidden units, but hidden neurons could be polynomials, and those are fixed because we know they're useful for the things that the outputs will do. But in other cases, we need to learn these in a multi-layer network. So again, whether the prior data is often encoded in the representation. and the representation represents the metric, and the metric tells you something about the observer. So then we go on to different types of learning. There are this idea of supervised learning, and we'll talk, he gives the structures for supervised learning. There are structures for reinforcement learning, and there's structures for unsupervised learning. And if you look at the differences between these things, supervised learning means you know you have an input X, you have an attempted output, and you have a correct answer. You have, in reinforcement learning, you have an input X, you have an output Y, which is usually a movement, and you have a reward that tells you what will happen. And what you're trying to do is predict the reward as a function of where you are and where you're going. Right? In unsupervised learning, is basically about finding the statistics of the input and creating a useful representation for something that will happen. And what you generally know, what the teachers know, is how is that output going to be used. He talks about the various types of tasks that can happen. So these are the types of algorithms, and there's many more, but those are the basic ones. But what are the tasks? You could do pattern association. That's input to output, y equals f of x, right? So we're associating inputs to output, or completion of a pattern. I have a degraded version of x, and I'm trying to complete it. I have, half an image, and I want to create the whole image from it. There are things, holographic memories, where early versions of this content addressable memory is a similar kind of idea, but the idea that I can index a whole picture from a half a picture, or a whole picture from a degraded version of it, and reconstruct it from memory. There's pattern recognition. That's where you have, the discrete set of classes. Here's my dogs, here's my cats. I want to classify this. It's a big reduction in information content, because I take all of these inputs, and there could be thousands of input dimensions, and I reduce them to a few binary pieces of information, right? So maybe that's a 1, that's a 0. The whole thing gets reduced to binary, so it's a huge dimensionality reduction. The difference between many of these is between supervised and unsupervised is whether the teacher knows the outputs or just some property of the output. So for instance, this is what the teacher knows. In supervised learning, the teacher knows the output. In unsupervised learning, the teacher knows some property of the output. It's smooth, it represents high variance, it represents high information. In reinforcement learning, the teacher knows the reinforcement. How much you're going to be paid if you do this in that situation. So the teacher or the environment gives you certain types of information. This is really at the algorithmic level. The implementation level of these things can be very similar or very different. You can use different kinds of algorithms to do different kinds of implementations for algorithms that accomplish different kinds of learnings, or different kinds of learnings, or different types of computation. Probably, actually, now that I think about it, it would be best to think of these things, the way I'm talking about it here, as being Mars computational level, almost the top level. What am I trying to do? Am I trying to learn a pattern matching task, or am I trying to learn a pattern in the data, or am I trying to learn how to act? And then I have an algorithmic model, which says, am I going to use an LMS algorithm or a TD Lambda model or something like that? And then I have an implementation level, which is this on a von Neumann architecture or a neural network? So those might be different. He talks a little bit about application to control theory. The same thing happens. There are different parts that can be learned, and often you have a state, a desired state, an error, and you have commands to plants, and all of these things can be learned in different ways depending on the information you have available. And there's different types of algorithms, and these are 3D. Experience learning is not a real term. The idea is you try something, you see what happens, you say, okay, if what happened is what I wanted, that's what I should have done. Right. So, and you can talk about different kinds of learning algorithms and control architecture. I'll use control algorithms from time to time, but I'm not going to expect people to know much about control. So I'm going to end the lecture there, and like I say, at 3:15, I will log on to the Zoom, which is in the Zoom link. Will always be the same. It's my personal Zoom, and it is in the syllabus. So log on there, and I'll be on. I can answer questions about this. And then, as I said, for the next class on Thursday, you should read this chapter, but the next chapter on perceptrons as well. And then there's the homework is problem 1.3 in that. So I look forward to meeting you and talking to all of you. You can certainly email me with questions. See you soon. Thanks very much.